In this lecture, we discuss some more examples based on the Lagrange's mean value theorem. So before solving the example, let us first see what is Lagrange's mean value theorem. Let fx be function of x defined in the interval ab such that f of x is continuous in the closed interval ab. Second, f of x is differentiable in the open interval ab. And third, f of b is not equal to f of a. Then there exists c in the open interval ab such that f dash of c is equal to f of b minus f of a divided by b minus a. So now we apply this Lagrange's mean value theorem and solve the next problem. The question is, prove that if 0 is less than a is less than b, and b is less than 1, b minus a upon 1 plus b square less than tan inverse of b minus tan inverse of a, which is less than b minus a upon 1 plus a square. Hence, so that pi by 4 plus 3 upon 25, which is less than tan inverse of 4 by 3, which is less than pi by 4 plus 1 by 6. So now here there are two questions. The first question is the fundamental part, which we have to prove this one. And after that, the second question can be deduced from this fundamental problem. So now here we have to use the mean value theorem. And for the mean value theorem here, it is very simple. Function is given tan inverse of b minus tan inverse of a. Because we have already seen that in mean value theorem, is Lagrange's mean value theorem, there is a upper limit and lower limit, or the interval has lower part and upper part. So here a and b are the lower and upper value of the interval. So tan inverse of b minus tan inverse of a is the part of the values of the function at upper limit as well as lower limit. So let f of x is equal to tan inverse of x. How we are able to recognize f of x is tan inverse of x? Because of this tan inverse of b minus tan inverse of a. Let us differentiate this with respect to x. We have f dash of x is equal to derivative of tan inverse of x is equal to 1 upon 1 plus x square. Now, by Lagrange's mean value theorem, we have f of b minus f of a divided by b minus a, which is equal to f dash of c. F of b means we have to put x is equal to b over here. So f of b is nothing but tan inverse of b, and f of a is tan inverse of a divided by b minus a, and f dash of c, we have to put x equal to c over here, 1 upon 1 plus c square, where c lies between a and b. Let us give it equation number 2. Now, we have again given one very important condition. 0 is less than a is less than b, and b is less than 1. So let us take to prove this result. Now we have a is less than c and c is less than b, because c is the value of x, which is obtained by using the Lagrange's mean value theorem. So clearly a is lower limit, b is upper limit. So now if A is less than C, C is less than B. So if we square it, then A square is also less than C square and C square is less than B square. If we add 1 to each and every term, then definitely 1 plus A square is less than 1 plus C square, and 1 plus C square is less than 1 plus B square. Now if we take its inverse, then this less than sign will be changed. It will become greater than sign. So 1 upon 1 plus A square greater than 1 upon 1 plus C square, which is greater than 1 upon 1 plus B square. Let us just start from 1 upon 1 plus B square, 1 upon 1 plus B square, which is less than 1 upon 1 plus C square, and 1 upon 1 plus C square is less than 1 upon 1 plus A square. Now, from the equation number second, 1 upon 1 plus C square is nothing but tan inverse of B minus tan inverse of A upon B minus A. Let us put the value of 1 upon 1 plus C square is tan inverse of B minus tan inverse of A upon B minus A. Now, multiply whole inequation by B minus A. Then it is B minus A. If you multiply this term, then B minus A will cancel. So we have only tan inverse of B minus tan inverse of A. And again, if you multiply here B minus A, so it will become B minus A upon 1 plus A square. So therefore, B minus A upon 1 plus B square is less than tan inverse of B minus tan inverse of A, which is less than B minus A upon 1 plus A square. So this is our desired result. This is our first fundamental result. Now, using this fundamental result, we have to prove the another thing, which is also obtained by putting some value of B and A in this particular formula. Putting A equal to 1 and B equal to 4 by 3 into means 3, not 2. We have B minus A. This is the given expression. We want to put B equal to 4 by 3 and A equal to 1 in this expression. So what will happen? B is 4 by 3, A is 1 upon 1 plus 4 by 3 whole square, which is less than tan inverse of 4 by 3 minus tan inverse of 1, which is also less than 4 by 3 minus 1 upon 1 plus 1 whole square. 4 by 3 minus 1 is nothing but 1 by 3 and 1 plus 16 upon 9, which is less than tan inverse of 4 by 3 minus tan inverse of 1 is nothing but pi by 4, 45 degree. So we can write down it is pi by 4, and this is less than 4 by 3 minus 1. So 4 by 3 minus 1 can be written as 4 minus 3 by 3 means 1 by 3. So now if we simplify it, 1 plus 16 by 9, 1 plus 16 by 9, this can be written as 9 plus 16 upon 9, which is equal to 25 by 9. 25 by 9, and 1 upon 3 is in numerator. So 1 upon 3 will cancel and 3 will goes to numerator, which is less than tan inverse of 4 by 3 minus pi by 4, this one, and 1 by 3 upon 1 plus 1. So 1 by 3 upon 2, so 1 upon 6. Now, if we add pi by 4 to each and every terms, then 3 upon 25 plus pi by 4, tan inverse of 4 by 3 plus pi by 4 and minus pi by 4, which will become 0, which is less than pi by 4 plus 1 upon 6. And this is our result. So in this manner, we are able to apply the Lagrange's mean value theorem, and we can prove some fundamental result. And with the help of that fundamental result, we are also able to get some particular result of the given function. Thank you.